Okay, so this is a non-calculator question, and this was the assignment for the tabular and the Riemann sum. And here we're given a table that is the height of a tree at a given time t is given by a twice differentiable function h, and where h of t is measured in meters, and the selected values of h of t are given in the table above. Okay, so these are all given values. So the first question here says, use the data in the table to estimate h prime of 6, and using the correct units, we want to interpret the meaning of h prime of 6 in the context of the problem. So first of all, for part A, we don't have 6, so we have to use the values that have 6 in between. So we want to calculate h prime of 6 is approximately h of 7 minus h of 5 over 7 minus 5. So h of 7 is 11, h of 5 is 6 from the table, and this is over 2. So what we have here is 5 over 2. Okay, so in this case, 5 over 2, or 5 halves, or 2.5, is the rate of the height of the tree per year. So the rate of the height of the tree per year. Okay, so it's the height per year, and that is represented by the slope. Okay, so in part B, it says explain why there must be at least one time t for the given time interval from 2 to 10 such that h prime of t is equal to 2. Okay, so we had a problem like this in our example problems, and this is an example of the MVT. So let's state first what was given before, that this is a differentiable function, which means that h of t is also continuous. So we would say that h of t is a continuous differentiable function, and it must be stated on the time interval from 2 to 10. So we'll just say like this, or you could say it like this. Whoops. Okay, on. Okay, so then what we have to do is calculate, what do they want? H prime of t being equal to 2. So what we had to look at were some of the points in between. So we had to go through and calculate. So I could say 11 divided by, well, we know here this is 5 halves, so it's not equal to 2. So we could say 15 minus 11, which is 4, over 3. That's not equal to 2. So what you do is have to calculate each time interval and see when you get a slope of 2. So when you look here, you have 6 minus 2, which is 4, which is in the numerator, divided by 5 minus 3, which is 2. So that gives me the slope of 2. So what we would say here is h of 5 minus h of 3 over 5 minus 3. And then from the table, h of 5 is 6 minus 2 over 2. So then we have 4 over 2, which is a slope of 2, which would be h prime of t. So then we could say, therefore, by the MVT, there exists at least one value t such that h prime of t is equal to 2 on the interval from 2 to 10. Okay? All right. So part C. Here it says, use a trapezoidal sum with 4 subintervals indicated by the data in the table to approximate the average height of the tree over the time interval. So first of all, let's talk about the trapezoidal. So back in the beginning of Unit 5, I showed a method where we could calculate the trapezoidal using literally a trapezoid method. The problem here is that my subintervals are not the same. 2 to 3 is 1, 3 to 5 is 2, 5 to 7 is 2, but 7 to 10 is 3. So we literally have to calculate the left and the right and then divide by 2. So let's do that first. So we're going to say L sub 4 is equal to 3 minus 2 times 1.5 plus 5 minus 3 times 2 plus 7 minus 5 times 6. Okay, and what we get here when we calculate is 50.5. Then I need to, so I'll need this is my left, need to calculate my right, R sub 4. Okay, so now what we've got is 10 minus 7 times 15 plus 7 minus 5 times 11 plus 5 minus 3 6 minus 2 times 2. Okay, and you need to make sure you're set up here, and this is equal to 81. Okay, so now to find my trapezoidal with subinterval 4, so t sub 4 is equal to 50.5 plus 81 divided by 2. So 50.5 plus 81 divided by 2. I got 65.75. Okay, so this is my trapezoidal, but the question says to approximate the average height. Now, in Unit 6, we started talking about the average value, and to find the average value, now this is where you might have gotten snagged up, this would be equal to 1 over b minus a times the integral from a to b. Okay, this right here is going to represent the area under the curve that we calculated right here. So 1 over b minus a is actually going to be the interval from 2 to 10. So this is 1 over 10 minus 2 times 65.75. So this is where we get 1/8 times 65.75, or this over 8. And remember, this is in meters. Okay? The last so it says the height of a tree in meters can be modified by the given function. So g is the height of our tree, and it's g of x is equal to 100x over 1 plus x, where x is the diameter of the base of the tree in meters. Just making some notes to myself. Meters. Okay. When the tree is 50 meters tall, so when g is equal to 50 meters, the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. So remember, x is the diameter, so this is a rate. So we're saying that dx dt is equal to 0.03 meters per year. According to this model, what is the rate of change of the height? So they want to know dg dt with respect to time in meters per year at the time when the tree is 50 meters tall. Okay, so we have dx dt, we have dg dt, or we want dg dt, we have g. So we need x. So the way we find x is g, which is 50 meters tall, is equal to this formula here. So we can actually find x by doing a little side work here by saying 50 is equal to 100x over 1 plus x. We want to solve for x so that we have all of our all the values for our variables that we need. So we're going to cross multiply, and when I do, I will distribute the 50, which is 50 plus 50x is equal to 100x. Subtract 50. So that means x is equal to 1. Okay, so we have dx dt, we have x is equal to 1, okay, and we have g, and we want to know dg dt, which means we actually have to take the derivative. So this is a related rates problem. So this right here would be dg dt is equal to, Now, this we have to use the quotient rule, and we also have to use the notation of dx dt when we're taking the derivative of x with respect to time. So when we take the derivative using the quotient rule, it's the derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. Okay, which is 100 dx dt. Okay, that's the derivative of the top times 1 plus x minus the derivative of the bottom. This is 0 plus the derivative of x with respect to time is dx dt times 100x. So we have 100x dx dt all over 1 plus x, the quantity squared. Now, I have to make a substitution in order to figure out what dg dt is, so I'm going to actually divide a few things out to simplify this just a bit. So this is one big term, and this is one term, so I'm going to factor out the dx dt. So what we have here is, and I'll distribute the 100 when I take this out, 100 plus 100x minus 100x times dx dt over 1 plus x, the quantity squared, and this is dg dt. So these go away. Okay, we have dx dt, and we figured out what x is. So now we can figure out dg dt, which is going to be in meters per year. So dg dt is equal to 100 times 0.03 over 1 plus 1 squared, which in this case is going to be 3 over 4 meters per year.